morning, good afternoon, or good evening, everyone, wherever you might be. So today we're going to be talking about the application of dot products. And one application that we're going to be talking about is this concept of work, which comes in physics. And so, yeah, let's just dive straight into it. So actually, um, one use of projections in physics is calculating work. And we defined work done. Oops, don't know why that happened. We defined the work done by constant force F. F means force. That's basically what it is. In moving an object through a distance d. And so this equation here states that the constant force F times the distance d is equal to its work. And well, this only applies when force is directed along line of motion of object. So what do we mean by that? Well, let's say this is your force, right? This blue arrow, you can already see it's blue. It's moving kind of in the same positive direction as this object is moving from P to Q, right? And so that's how this is going to work. And what we're going to do here is the constant force F is going to be a vector. So we're going to make this a vector from P to R, from P to R. That's going to be our vector F. And again, the force moves the object from P to Q. So from P all the way to Q. And therefore, we have this thing called displacement vector, which is D. So that's the one in green. The red vector, that's the projection of F. But D is the displacement vector from P to Q. And so we came up with this formula where work is basically equal to the product. So that's a product. We have this times this. And the first thing is that vertical lines in F times cosine theta. And that's basically the component of force along D. So what do we mean by that? Well, from our previous example, not sure if I showed this in the last video, but I'm going to show it anyway. We talked about this thing called projections. And this is the idea of, let's say you have a vector B here, this vector B, and you basically have like some sort of shadow, which is this red vector. And it's the same idea in this example here. So when we have that vector that kind of goes up, we have like this vector that goes up. We have this red vector that goes down. This is like a shadow, right? Let's say there was a sun and it's kind of pointing there. So that's the shadow. The red vector is basically the shadow. And we call that a projection because hence the word, it projects what B is. And same idea here in this example, right? If you put the sun maybe around here or a flashlight and whatnot, it's kind of going to reflect B. It's going to project B, and we're going to have this vector. So that's the idea. And the scalar projection, and we call it the component of B along A, what that basically means is the projection's length. That's what it means. So let's say we have this, we see here, right? We have these red arrows. How long are they? You know what I mean? That's what the scalar projection is for. And hence the word we have scalar, because we're scaling, we're multiplying, because we want to get the length of that projection. And so here, that's the length. And we can see the length is this absolute value of this vector, or the length of B, times cosine. Now, why cosine? Well, this came from this right here. Pretty sure we talked about it in the previous video. which is this idea of the law of cosines. That's how we were able to get this formula here. And what we're saying is this is the, if you look at this formula here that we came up with, this is A times the scalar projection of B onto A, right? Because this is the scalar projection of B onto A, and we're multiplying it length of A times, which is this one. Okay, a lot of me talking, but we'll get through it. And since this scalar projection of B onto A is actually equal to the dot product of A times B divided by length of A. How did we get there? Well, if you look here, A times B, right, this one, we equate it to this one, the absolute value of A times the absolute value of B times cosine theta. And actually, what we can do here is we can divide both sides, right, by the length of A. And if we do that, well, we're canceling this one out and we're left with this. So we have this is equal to this. And hence, that's how we got that there. And funny enough, we can actually translate this in pure English. And what this basically means is if you look at this thing here, the component of B along A can be computed by taking the dot product of B with the unit vector in direction of A. So this is the dot product A times B. And the unit vector is this, right? It's basically the vector itself divided by its length. And that will give us 1. Remember from our, pretty sure it was the previous chapter about vectors, where we talked about unit vectors. And that's the idea, right? And here, this is where we got our final formula. So scalar projection and vector projection. Okay, moving on. We did a little example here, but I'm not going to go through that because honestly, it's just plugging in the formulas. Now we go through work. And again, application is physics, calculating work. And the formula for work basically is this thing. This is work, which is equal to the force acted on the object times the distance that the object traveled. Oops, I shouldn't have deleted it. There we go. And again, this only applies when force is directed along line of motion of object. So they're kind of in the same positive direction right there. And here we suppose that the constant force is F if the force moves the object from P to Q, and that's the displacement right here. And from theorem 3 is about law of cosines. That's basically the dot product is the length of A times the length of B times cosine theta. So here what we're saying is the dot product of force times displacement is the length of that force vector times the length of displacement, and this basically means distance, believe it or not, is cosine theta. So that's what theorem 3 is about. Okay, now we go to an example before I start yapping. A wagonist pulled a distance of 100 meters along a horizontal path by a constant force of 70 N. N means newtons, right? And it says here, the handle of the wagon. See if I can write this quickly. The handle of the wagon is held at an angle. 35 degrees, right? Above the horizontal. So pretty weird wording if you ask me. But it came from my textbook, so we'll we'll get past it. And our task is to find the work done. By the force. Force be with you. Sounds like Yoda. Okay, and I'm going to take a screenshot of the figure just so that we can understand it better. Oops. Okay. I'm going to take a little copy paste here. There we go. So yeah, here we have the wagon. And I think the horizontal that it's saying is this horizontal right here. Oops. And now I can get back to my, oh, there we go. The horizontal, it's this one. That horizontal. Okay, anyway, let's go through it. Okay. So, what's the first thing we want to do? Well, if we want to calculate the work, we already have a formula for that, which is this piece right here. Right? If you want to find the work done, we just have to find the dot product of F times D. But since here we're given the information about the angle, then we might consider using this formula right here, right? Oops, I deleted some of them. Okay, so we want to make use of that formula. So our work done, yeah, we're making use of this formula, is the length of vector F. And what's the length of vector F? We kind of have it, which is 70. What's our distance? Or the length of vector D? And it says here it's 100. Let's pull the distance of 100 meters along a horizontal path. So we're going to make use of that. Cosine. And what's our angle? 35, right here. So again, we will make use of that. And now, what is this value? Well, we're going to calculate that. So we have 70 times 100 times cosine of 35. And we get approximately 5734 Newton meters, which is just joules. And so that's the work done. Now, don't ask me any physics questions because I haven't studied physics before. I probably did, but I didn't listen to my physics teacher when I was in high school. So anyway, yeah, we're done with the task. Boom, finished. 5,734 joules. Yeah, that means joules. Okay, now we move on to our next task. Or I mean our next example, which I think is our final example. And we're saying here we have a force that is given by a vector F. And we have our components. Our components are in terms of ijk. So 3i plus 4j plus 5k. And moves a particle, the typical physics question about particles. And moves a particle from point P. What's point P? 210. To another point, Q. What's that point? 462. And we want to find the work done. Okay, right. So how do we do this? Well, again, we have to find, but we have to make use of this formula. F d cosine theta is dot product of f times d. But if you notice here, yeah, so the reason why we're using this formula is we want to find the work done, obviously, right? But if you notice here, there's no information about angles. So most likely, we're using the dot product of f and d. And we're actually already given f, if you think about it. We're already given f. F is this thing. That's it. We're given f. Now we want to find d, or displacement. How do we do that? Well, we want to find the vector pq. And so basically we want to see their changes, right? We want to subtract q or p from q. So the way we can do that to find d, or actually let's do it step by step. We have p, this point, and q. We're basically subtracting each of their values. So we're subtracting this from, or the other way around. This minus this for the x component, this minus this for y, this minus this for z. And so from there, our displacement is just going to be a vector. That's 2, 4 minus 2, 2, 6 minus 1, 5, 2 minus 0, 2. That's it. Okay, and then now we just plug it in. We now have a formula for both. Our f is this piece right here. That's 345 times 252. And that's it. We just apply dot product. 3 times 2, 6, plus 5 times 4, 20, plus 5 times 2, 10, 26 plus 10, 36 joules. Boom, finished. Yeah, and that's it for today's video on finally I finished dot products, and I'll see you all in the next one.